Last time we considered examples of p-series. Let's consider a new example to start our discussion of series today. Let's consider the series n starting actually at 2 and going to infinity of 1 over n times natural log of n. We're wondering, does this series converge or not? And if it converges, could we possibly figure out what it converges to? Those are two separate questions. And the second question is much, much harder than the first. It's in general much, much harder to figure out what a series converges to, even if you know it converges. Not a problem typically to approximate what it converges to, but to figure out exactly, like with the p series when p was 2, was pi squared over 6, right? That took Euler's genius to do that. None of us are at the level of Euler. Not me either, okay? So it's a much, much harder question, but sometimes we can. Geometric series you can. There are going to be some other examples in chapter 10 where you can. But mostly we can't. We're going to be satisfied with deciding, does this converge or not? Now, this one's a little unclear. If we think about comparing this with what we know from p-series, think about a typical kind of p-series here. We know that, for example, the p-series when p is 2 does converge to pi squared over 6. We also know that that converges if the p is even slightly bigger than 1. If I change this p to 1.1, it still converges. If I put a decimal in there like that, Mathematica is going to give me the answer as an approximation. If I did not put this in here as a decimal, but as a fraction, probably Mathematica is going to return a zeta value, zeta of 11/10. Or that's the zeta function. We're going to talk more about the zeta function next week in some interesting ways. We're after just an approximation. Putting a decimal in there is good. What if it's just barely, barely bigger than 1? Like that. Oh, it still converges. Although that number is 1 million. Is the answer exactly 1 million? No, I'm sure that's just an approximation. Add in a few more zeros and we might get 1 billion or something. Yeah. Even if p is just barely bigger than 1, these series converge, but they converge to big things because the terms that are being added go to 0 very more slowly. If p equals 1, that's the harmonic series, and you should know for the rest of your life that the harmonic series diverges. This is so small it's not readable, but it says sum does not converge. But what about this one here? Where the bottom is n times natural log, log is natural log. Mathematica claims does not converge, or okay, I have to start at 2. I don't want to start at 1 because ln of 1 is 0. I don't want to divide by 0. Mathematica says sum does not converge. So I guess we know the answer if we trust Mathematica on this. But is it really right? We can use the integral test. Let's prove divergence with the integral test. Now, if you didn't know the answer, either because you didn't have something like Mathematica available or because you just didn't trust it, you wouldn't know that you're going to prove convergence necessarily. You might be proving divergence. The method is still the same. You still effectively integrate the terms, though for conceptual clarity, change the variable name to x, say, to emphasize that you're going to do an integral with respect to a continuous variable x. And it is a discrete variable, taking on positive whole number values, in this case, 2, 3, 4, 5, 6, etc. You wouldn't think about integrating that kind of thing. But the goal with the integral test is to define your quantities like an to be 1 over n times ln of n, and f of x to be the same thing except use an x instead of an n. Conceptually, that's still helpful, though, To, in your mind, remind you n is discrete. We typically think of n as discrete, and x is continuous. We typically think of x as continuous. So make those definitions. Note that an equals f of n. If I replace x with n, then I get the same thing for all n of concern here, 2, 3, 4, 5, 6, etc. For other values of n as well, but those are the values of n that we care about for the summation. We should also note that f of x is positive and decreasing for all x greater than or equal to 2. Why should we say that? Because it's part of the integral test. Part of the hypotheses of the integral test is your f of x needs to be a positive function whose graph is above the axis and decreasing over the interval of concern. If you use your calculator, you'll see a graph like that. It could be increasing other places, but we only care about it being decreasing there. It also is continuous there. You do want to avoid near 1 because you got a vertical asymptote at 1, because ln of 1 is 0. But this is all we care about. And what do you do now? You do the improper integral of f of x. If this improper integral converges, the integral test would say the series converges. If this improper integral diverges, the integral test would say the series diverges. So it's a very nice test that way, and integrals are easier to compute than summations. Question? Yes, thank you. 2 to infinity. But remember, improper integrals themselves are defined to be limits. When the upper limit is infinity, you make the upper limit the letter b, say, and you let b go to infinity in the end. Now, this looks like it could be a difficult integral to do. It's not too bad. You can do a substitution. Let w be natural log of x, then dw is really sitting there for you. It's 1 over x dx. I purposely made it work out nicely. So it's kind of phony in that way, you might say, but it does work out. It's a good example still to talk about. So I'm not using integration by parts, I'm using substitution. And remember, it's with substitution that you have to change the limits of integration. When x is 2, w will be ln of 2. When x is b, w will be ln of b. And I'm going to be integrating 1 over w dw, giving me yet another natural log. This will be the limit as b goes to infinity of ln of, well, okay, if we want to put the absolute value signs in there, that's okay. Absolute value of w goes from ln of 2 to ln of b, where you would be assuming b is bigger than 2, and so then ln of b would be positive, so I can get rid of the absolute value signs, as we often do, though you should think about that each time. So we take the limit as b goes to infinity of ln of b, and that's no joke, ln of b, minus ln of 2. ln's within ln's. Now, ln of 2 is a constant. In fact, it's a negative constant. It's about negative 0.3665. But we don't really care about that so much. We're more interested in what's the limit as b goes to infinity of ln of b. ln of x goes to infinity, though very slowly. So slowly that it looks sometimes like it might have a horizontal asymptote. Does that still go to infinity? Yes, it does. As b goes to infinity, ln of b goes to infinity, which means ln of b goes to infinity. but super duper 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 slowly. How big would B need to be, for example, for ln of B to just say be bigger than, oh, how about 5? If this is going to be true, that's equivalent to ln of B itself being bigger than e to the 5th, which is equivalent to B itself being bigger than e to the 5th. So just to get bigger than 5, you got to be bigger than e to the 5th, which is 2.85 times 10 to the 64th, just for this function to get bigger than 5. 2.85 times 10 to the 64th. How big does it need to be bigger than 6? E to the 6th. Overflow. It's bigger than 10 to the 100. It's bigger than a Google, just to get higher than 6. But you can get higher than any number if B is sufficiently high. It would definitely look like it's got a horizontal asymptote, but it doesn't. This does diverge to infinity. I'm going to go ahead and write an equals infinity here, though I'm not saying infinity is a number when I write that. I'm saying this thing diverges and gets arbitrarily large. And that is enough to say the improper integral diverges, and therefore the series diverges. Therefore, series n goes from 2 to infinity of 1 over n ln of n diverges by the integral test. We're done. Praise the Lord. So even though we're dividing by something bigger than n times ln of n, in fact, it's n times something that does go to infinity, the fraction still goes to 0 slow enough that the series diverges. The fraction, meaning 1 over n ln of n. That's still a sequence of terms that goes to 0, making it still a question. Maybe the series does converge. But no, this test shows it diverges.